Yeah, we good to go? Yeah. Okay, so welcome everyone to the fifth and final lecture on indirect detection. We swapped around the order a bit because I think the discussion will be more interesting if we've had the full lecture series before we get into it. So I will be continuing straight on from what we were talking about this morning. So the goals for this section, we already talked about, we talked a bit about backgrounds, we talked a bit about the upcoming experiments, we talked a bit about the cosmological constraints. So where I want to go next is continue talking about the current leading indirect detection constraints for annihilation and decay across a range of dark matter masses and final states. And then in the latter part of the lecture, I want to talk about current things that we do not understand in the data. So anomalies or excesses and what the proposed explanations for those might be and a bit of how we might make progress on them. Okay. Okay, so going right ahead. All right, so we talked this morning about cosmological constraints, and I said that these cosmological constraints being essentially calorimetric, they're mostly just measuring the amount of energy transferred into the universe by dark matter annihilation or decay, are very model independent. So they don't, subject to the caveats that we talked about earlier, that there are some models that are just really hard to see in indirect detection and some models that are easier. So this means that because those cosmological constraints do not rely on being able to directly observe the products of the annihilation or decay, they give us a backstop that doesn't really depend on whether we have a telescope in the right energy range to see the annihilation and decay products. But if we do have a telescope in the right energy range to see the particles from annihilation and decay directly, then those constraints can be quite a bit stronger. So let's now, I want to look at some of those now. This follows nicely from what Annika was just telling about. So in particular, the dwarf satellite galaxies, the Milky Way, are low background environments and relatively nearby, which means, as we talked about this morning, they have moderately large J factors. And the expected gamma ray emission from baryonic physics in the dwarfs, the expected gamma backgrounds from the effects that we talked about this morning, like cosmic ray emission and stars emitting gamma rays, is approximately 0. So this paper from a few years ago looked at the probability of having an appreciable number of pulsars in a dwarf galaxy and found that the background was way below current sensitivity. However, we do live inside a galaxy, so when we look at the dwarfs, we have to look through the galactic halo to see them, and there is some foreground as a result of that. The other caveat about dwarf galaxy limits is that the uncertainties in the J factors can be substantial, so you need to marginalize over how much dark matter you think there is in a given dwarf. But taking that into account, dwarf observations can test the thermal relic cross-section for hadronic final states, so the ones that make broad continuum photon emission, for dark matter masses usually up to a few tens of GeV. So this is a reanalysis by Alvarez et al. In 2020, looking at a number of dwarf galaxies observed by Fermi and trying to do a careful analysis of the uncertainties in the foregrounds and in the J factors. If you are not quite as generous with them as in uncertainties in the foregrounds and the J factors, you can get a somewhat stronger constraint up to like the 100 GeV mark. So question here?
Yeah, thanks. When calculating the J factors for the dwarf galaxies, can you still use an NFW or INASI profile?
So people often do, but so there's been debate about this because there are some dwarf galaxies that there have been claims that they have a more chord profile. The thing is that because in the dwarf galaxies, you're usually looking at the total integrated emission from the whole dwarf, not just the emission from the very center. Like when we look at the center of the Milky Way, we're not looking at the signal from the whole Milky Way halo, we're just looking at the center. But for a dwarf, usually they're small enough that you're going to integrate over the whole thing, given the angular resolution of your instrument. And that means that the details of what's happening in the very center of the dwarf matter less, because most of the volume in the dwarf is in the outskirts regions, and often most of the signal is coming from those outskirts regions. So there are uncertainties associated with the profile, but they're often more like 20% uncertainties as opposed to the orders of magnitude uncertainty in the galactic center. That sometimes the bigger uncertainties are like, what is the profile doing in the outskirts of the dwarf? There aren't a lot of stars out there, so does it fall off like a power law? Does it have a longer tail? And so exactly how you model the profile can give you pretty different answers for the total J factor. But it's a good question. But I mean, there are big J factor uncertainties on the dwarf, but surprisingly, it's often not the behavior at the very center that is the uncertainty, in contrast to something like the Milky Way. Okay, so this plot up here, there'll be a lot of plots like this. This is showing the cross section that's constrained on the y-axis, the dark matter mass on the x-axis, This dashed line is a thermal relic cross-section. So of course, that's not a guarantee. We could have a cross-section that's larger or smaller than that, given the various kinds of models that we talked about earlier, but it's a convenient benchmark. So, and what this is showing you is that, so this is from a bunch of dwarfs combined. This is for one particular channel. So this is for annihilation into B quarks, but most of the other annihilations into hadronic final states will have broadly similar limits to this. And so you can see we said that for the CMB bounds, we're going to test this channel for masses, for the thermal relic cross-section for masses below about 10 GeV. But with these combined limits, we can get up a factor of a few higher than that. And if you didn't allow so much slack in the uncertainties, you could potentially claim limits more like 100 GeV than 30 GeV. So there's a factor of a few there.
There's a question on the like,
Wait.
wait a second.
I can hear you well, but
Yeah.
people.
Yeah, so if there's like uncertainty on this dashed line, I mean, how do you actually exclude models when you have from experiments? Because if you can shift the line, if you, I guess you change the coupling, you can shift the line.
So you change, right? So yeah, so you say whether or not you're testing specific models. So like, for example, for any model where the abundance is set by the thermal freeze-out mechanism, and the annihilation cross-section doesn't have any significant velocity dependence at late times, and the dark matter is symmetric, not asymmetric and stuff. For those models, the uncertainty on this line is probably relatively small. But so I can pick a different model, one that has p-wave annihilation or one that is asymmetric, and it may not be constrained in the same way by this plot, right? I just like for each model, I need to ask, you know, what is the appropriate constraint? Does that make sense?
Yeah, and then the coupling, like because you calculate a coupling when you choose a coupling when you have the cross section, is that right?
So
Or,
right, so if you gave me a Lagrangian, the dark matter, what I would do to apply it to this plot is I would say, all right, I'm going to take this Lagrangian and I can figure out by what mechanisms the dark matter can annihilate into B quarks. So I'd back down a Feynman diagram for that, which is a function of the coupling, and I'd also work out the cross section, the inclusive cross section for the dark matter to annihilate into anything. Now, if I require that the dark matter has the correct thermal relic abundance, then that will fix the coupling as a function of mass, because it'll fix the thermal relic cross section. Then I can take those parameters and because we know that the thermal relic cross section is almost independent of mass, that'll fix the thermal relic cross section to all channels to be around this dashed line. And so then I can ask the question of, okay, so the simplest thing I can do is say, what's the cross section to B quarks, and compare it to this gray constraint line, and that'll tell me if it's ruled in or out. But you might say, what if I annihilate a third of the time to B quarks, and a third of the time to like tau lepton, and a third of the time to something else? There's an earlier dwarf paper by Fermi from 2015, which actually provides the likelihoods on an energy bin by energy bin basis. So then you can work out the full gamma ray spectrum that you would expect from your model and compare that directly to the data. So what's been done here is that they have actual data points, the number of gamma ray photons for the dwarf galaxy. They compare that to the model prediction for this particular annihilation final state, and then they've translated that into a constraint on the cross section. But you can just go back to the raw data if you have a more complicated model. And but as I said, often and work out the constraint from there. But often for these hadronic channels, the limits are reasonably similar for different channels. So if I have a third branching ratios into 3 states that are all going to make hadrons and are all going to make neutral pions, I'm going to get a decent approximation of the limits by just sort of looking at, okay, what are the individual limits for each of these 3 and like taking an average. Now that may be different if I have a 50% branching ratio into like E plus E minus, which makes hardly any photons at all. Then I may need to think a little bit carefully about what the constraint should look like.
all right, thank you.
Good questions. Yeah.
If we have this foreground issue with these dwarf galaxies, would we be able to rule out the galactic center excess?
I think so, yeah. So my recollection is that the number of expected you would need to be careful about the J factor uncertainties, and be sure that you really confirm the J factor uncertainties. But at the moment, the GCE is pretty well. Those of you who don't know about the GCE, don't worry, we'll talk about it later. The GCE is kind of marginal compared to these constraints. It's like here, and so you would only need, like, if you could make them an order of magnitude stronger, you could rule out the GCE. My recollection is that with like GCE scale cross sections, if you ask how many photons would you expect from the like biggest dwarfs in Fermi, the number is like 20 or 30 signal photons. So if there was zero background and you were expecting to see 20 or 30 signal photons and you saw zero, that would actually be a pretty significant exclusion. If you're expecting to see that if you have a background of, 50 photons or 100 photons, then seeing 20 less than you expected may, doesn't let you set that strong limit. So my guess is that if there were truly no foregrounds, then we could, because it's close enough. But I haven't done the calculation in detail.
And do you have a rough feeling for how many gamma ray photons we can expect from the foreground?
No, but just that I think that other people in the room may remember, but my recollection is that so there were 1 or 2 dwarf galaxies where they saw what looked like maybe a 2 or 3 sigma excess at one point that was within the J factor uncertainties compatible with the galactic center excess signal. So that would have been a possible confirmation, except it wasn't very significant. It was only really like a 1 dwarf. But my recollection was that was about, as I say, my recollection was that was about 20 photons. And so if 20 photons was 2 sigma, you can sort of guess that maybe the foreground is like 100 photons, right? So roughly speaking. So I think that's broadly the ballpark. Like, I don't think it's 1 photon and I don't think it's 10,000 photons, but that's my guess.
Sure. And I guess where I'm finally trying to get with this is, I guess if we had high resolution, we could probably easily separate the foreground from the background, right?
No.
I can see how the light's coming in.
Maybe. So yeah, so this is saying if you have really good angular resolution and you can resolve the whole shape. So the idea would be like to, say like, is this compatible with an NFW profile or whatever from the dwarf? Like when the dwarf gets denser in the center, can I see how the emission falls off? And thus say that it's associated or not associated with the dwarf. Maybe, the question is basically how big it, like how much better would your angular? So yes, if you had completely perfect angular resolution, you could do that. You could do much better in foreground subtraction. But I don't know how far the dwarf is away that these dwarfs in this analysis are from being standard sources in Fermi. I think they're pretty close to point sources with the current angular resolution. I don't know how much you would need to make it better to change that.
In particular, I was thinking about using angular resolution on the foreground. If it's closer, I could expect them to be a little more dispersed versus something that's far away.
Yeah, so let me, if I write on the blackboard, then I guess the Zoom people will not be able to see. But so it's just like if we think about, so what you're looking at is, so, you've got this dwarf galaxy whose contours and emission look something like this, right? And you've got a foreground which has some variability because the gas clouds have some variability, and so you have some, so then you have like some contours of foreground emission. I'm not trying to say that it's shaped like the dwarf galaxy, just that it has some variability on scales which are probably larger than the dwarf. And yeah, so in the current situation, what happens is that basically, I suppose like this is sort of the size that you can resolve. So then you're not using the shape of the dwarf at all. You're just saying how many photons are there from this versus how many photons are expected from this versus how many photons are expected from all this messy stuff. So yeah, like if you can get it so that instead you're resolving things so that your effective pixels look like this, then it's not even a matter of like resolving the shape of the foreground. It's that just there's way less foreground in any one of these pixels, whereas you still have a lot of signal and you could try to map out the shape of the signal. So if what you're saying is like maybe with better foregrounds we would be able to like better with better angular resolution, we would be able to see predictable patterns in the foreground and like better extrapolated or interpolated across the dwarf. That's possible, but the foreground is pretty structured because it comes from, a lot of it comes from just like the distribution of gas in the galaxy, which does have small scale structures. So it's not a good assumption to say that the foreground is just completely constant across the whole region surrounding the dwarf.
Okay.
But it's a good question because the more spatial information can be super powerful in separating signals from backgrounds in this case.
Sure.
How does that those limits with the dark galaxies is from out of the scope?
Yeah, so these are observations. So these are observations of the dwarfs from the Fermi galaxy. Yeah, sorry, I thought I said this, but maybe I didn't. So these are observations of the dwarf galaxies from the Fermi Gamma Ray Space Telescope. So they're looking in the direction of the dwarfs, like doing this kind of analysis, and basically just saying, okay, I am going to try putting down a model of the dwarf in the location of the dwarf, which depending on the angular resolution of the telescope may essentially just be like a point source. And then saying, okay, I do a likelihood analysis and I ask, what does my likelihood analysis tell me is the upper limit of photons associated with this dwarf galaxy? Okay, and then that upper limit, so by the calculations that we did yesterday, if you've got an estimated J factor for the dwarf galaxy, then you have a theory, you can convert your cross section, which is sigma b, and your spectrum, which is BB bar, into a prediction for the number of photons. You can see from that, and you can confront that prediction as a function of those parameters, sigma b and m. And so typically you pick the mass, you pick the final state, you vary sigma b, you ask, okay, how many photons would I predict as a function of sigma b? When is that number of photons excluded at 95% confidence by the number of photons I actually observed? Okay. And when you hit that 95% confidence limit for an individual dwarf, you get a point on one of these green or red or blue lines. And then you can you can like multiply the likelihoods together from different dwarf galaxies to set a combined limit on the cross section. Okay. And so the way that Fermi typically presents their data from the dwarf galaxies is they look at the photons in energy. So there are multiple ways that you can do this analysis, but one way to see it is like just counting photons associated with the dwarf in each energy bin, or lack of photons associated with the dwarf in each energy bin. Because normally we don't detect any of the dwarfs in gamma rays. We just set upper limits on the number of photons that could be associated with them. Okay, does that make sense?
Yeah.
Yeah, there's actually a 2015 Fermi paper, which I can give you the archive number for if you're interested, which has a nice supplementary material which spells out the complete likelihoods by energy bin. And thus you can redo this analysis for alternative spectra. Which so it basically gives you the raw data that you can use to redo this. Okay, so that's one kind of analysis using gamma rays from Fermi and observations of dwarf galaxies to constrain the dark matter annihilation cross-section. And this we think is pretty robust because yes, there are uncertainties in the J factors, yes, there are uncertainties in the foregrounds, but the backgrounds are fairly manageable and we think we have marginalized over the uncertainties in the J factors. So if we had better J factor estimates like observations of more stars, then you could potentially make these limits quite a bit tighter as well. That's the other way to attack the problem. There are other limits of fairly similar strength from looking at other regions in gamma rays, again with the Fermi Gamma Ray Space Telescope, so from studies of the Milky Way galactic halo by Chang et al. In 2018, and by studies of galaxy groups. So this is galaxies and galaxy clusters extragalactic to the Milky Way. You find that you get pretty similar bounds in this around 10 to 100 GeV range for the thermal relic cross section. These searches have different systematic effects, and I would say probably like more significant systematic effects than the dwarfs, but they're very different systematic effects. So for example, for the galactic halo modeling, which model you use for the backgrounds and foregrounds, so for cosmic ray emission coming from the galaxy, makes a pretty big difference in the strength of your constraints. It doesn't matter nearly as much for the dwarfs. For the galaxy groups, survey questions about like the J factor and the boost factors associated with each galaxy or galaxy cluster become important, less important for the dwarfs. So the fact that all of these different analyses end up landing in more or less the same place in what kinds of cross sections you can constrain, gives us some confidence that probably something around that level really is the correct limit. As we go to higher dark matter masses, you might ask the question of, okay, so at higher dark matter masses, we may not be able to constrain this thermal relic cross section, but we can still set interesting constraints on sigma b, and that could be relevant for models where the annihilation rate is enhanced at late times for one reason or another, relative to the thermal relic value. And so this lower plot is showing some bounds. So this yellow line is the bound from the Fermi analysis of dwarf galaxies. You'll notice the y-axis on here only goes down to 10 to the minus 25. So these are larger cross sections. So this is that extrapolated Fermi limit, similar to this gray line. This is just an earlier version. And then these other colored lines are showing the limits on the annihilation cross section that can be set by a range of other ground-based gamma ray telescopes. The new limit in this work was from Hess, which is this black line. Okay, so this is what I mean by Fermi is king at the lower energies. As you go to the higher energies, you see Fermi actually does pretty well up to a few TeV, but eventually it just peters out and then these high energy, and then these ground-based telescopes take over. So these are what I would say are the robust bounds from gamma rays on dark matter annihilation. You can get much stronger nominal limits if you look at the galactic center and you think you understand all the backgrounds in the galactic center and you assume an NFW profile. But those bounds have much greater systematic uncertainties. Okay. So if asked the question of what does looking at dwarf galaxies tell us about dark matter annihilation, these plots are basically giving us the summary. They tell us the annihilation cross-section can't be larger than these lines. Okay, so what about then the cosmic rays, about charged particles? So these two plots here are showing two examples of data sets from the AMSO2 telescope. On the left, this is the flux of antiprotons divided by the flux of protons. So this is showing like an antimatter to matter excess. This is from 2015. I think this is a paper with, I think Marco, this is your paper and collaborators. And these plots and this plot on the right is showing the spectrum of positron, is showing the positron flux. So this is E cubed DNDE. The reason it's E cubed DNDE is because the underlying spectrum is similar e to the -3. So they're multiplying by E cubed to make it easy to see what's going on. So this is the positron flux spectrum as seen by AMS. And so this structure that we're looking at, where we have this sort of power law, this rising power law, and then this cutoff, this is interesting. We're going to talk about this later when we come to the anomalies section. We still do not fully understand what is causing this behavior. But so these are examples of the kind of data that AMSO2 gives you, the energy spectra of antimatter. Yeah.
I think I just missed this. Are these plots combining the antiprotons and positrons?
Plot on the left is ratio of antiprotons to protons.
Okay.
Okay, so that's one thing. Plot on the right is just flux in positrons.
Okay.
I'll show you the electron flux as well later, but these are just, to give you an indication of sort of what the data sets look like. And I'll just note, like over here, you see in both of these, the error bars are really tiny at low energies. Like at low energy, we have really high statistics. The error bars are very small. We can actually see pretty precise features in the spectrum. At high energies, the reason these error bars are becoming large is because there are just not that many, TeV positrons that AMSO2 sees. Okay, so statistic, this is generally true for these 100 GeV scale indirect detection searches. The statistics drop off fast with energy. So it's always true that looking at lower energy stuff is going to give you stronger constraints. Other things to note in this plot. So this colored band here is a set of background models for the signal that we expect for antiprotons just coming from protons hitting the gas in our galaxy. And these bands are supposed to show the systematic uncertainties in those background models. So this is using exactly the kind of formalism that we talked about yesterday, solving a diffusive propagation equation for the galaxy, modeling some injection of protons from supernovae throughout the galaxy, looking at how they diffuse and what antiproton flux they produce. Okay, so you will note that here there's not a great difference between the proton data point, between the antiproton data points, which are these black dots, and the expectation for the models. So that means we're going to be able to set limits, and actually pretty strong limits on additional contributions. But you also see that like this band is really large compared to the error bars. This also tells you that the limiting factor for setting limits from cosmic ray observations is typically going to be these propagation uncertainties. So this is always kind of the key question when looking at cosmic ray searches, what are they assuming for the propagation uncertainties? What have they done to make sure those uncertainties are properly probed? Yeah, question?
How do these points, they can vary, depend on your observational time? Like, if you have more time for observation, like these points would change?
If I had, good, okay. So there are things that can make the points vary over time, most notably for the, I talked earlier about solar modulation. So these are all observations taken in the neighborhood of the Earth. They're looking at charged particles that have had to get to us through the solar wind. So as the sun's magnetic field changes, that can modify the spectra, especially at low energies. So there can be a time dependence in that sense. The time scale is the solar cycle. If you were able to take those effects out, though, what you expect is that as time goes on, basically the central values should stay similar, but the error bars should shrink. Okay. But I mean, this is, so like, I mean, this is a ratio. So as time goes on, you know, like you'll get more antiprotons, you'll also get more protons, they'll cancel out. This plot is a flux expressed in GeV squared per square meter per second per steradian. So it's sort of like the observation time has already been divided out. So this is like, events per square meter of your detector per steradian of the sky that you're looking at per second of observation time.
My question is if your page could change with time, like you could see a bigger weighting like in the proton ratio. If you get more time to observe.
You could see a more significant increase. So like, suppose that over time, these points stayed exactly where they were, but these error bars shrunk by a lot. Then maybe you would say, aha, this point is possibly in excess. Maybe it's telling us something interesting. All right, but like you wouldn't naively expect the central value to change outside the error bars. Like the error bars are supposed to be telling you roughly what the uncertainties are on the central value.
Yeah, and maybe it's a basic question, but I don't, why are the limits quoted here in energies? And the previous slide, they quoted in terms of cross-section and dark matter mass?
Yeah, it's because on the previous slide, I was showing you the limits that had been derived from the raw data, and here I'm showing you something closer to the raw data. I'll show you the limits on the next slide. So yeah, so the questions that people were asking previously, which I can't go back to, okay, about like how that limit on cross-section is derived. Is you look at a spectrum like this coming from the dwarf galaxies, you say, okay, I have a model for my signal, which say looks like this, and then I vary the size of my signal until it's too large compared to the data, and then I say that it's excluded. Okay, so here we're just looking at the data. Like here we're just looking at in each of these energy bins, how many antiprotons do I have compared to protons? And you can see the scale is about 10 to the minus 4. So I have a lot more protons than antiprotons, but you know, that's fine, that's normal. There's a lot more matter than antimatter in the universe. This plot, so this is just, but if we had, a dark matter signal should produce equal amounts of antiprotons and protons. So if we had a huge dark matter signal, we would expect this ratio to start going much closer to 1/2. And so on this side, this is just showing the observed number of positrons in each energy bin. But rather than just plot like number of particles per energy bin, which would be dNdE, they've multiplied here by the energy of the particle cubed, just because otherwise this would be like a steeply falling on a log plot and it would be hard to see the features. So they've multiplied by E cubed so that you can see the features more clearly.
Okay, thank you.
Yeah,
Thank you.
Good. No, don't worry about asking basic questions. Like it's good to understand this stage.
Right.
That's it's definitely better to understand. And yeah, my general impression is that if one person is confused about something there and is willing to ask a question, there are probably 5 other people in the room who are also confused about it and haven't formulated the question yet. So keep asking questions. That's very good. Okay. So yeah, so now let's take those data sets that we looked at on the previous slide. So these are observations of the amount of antiprotons and the amount of positrons in AMSO2 data, and ask what does that look like once we convert them into a limit on the dark matter cross section. So again, the way we do this is we're going to take a model with some mass scale, some final state. We're going to figure out the spectrum of positrons and antiprotons and protons that are produced by the dark matter annihilation. We're going to propagate those spectra through our galaxy by running some kind of diffusive propagation code using the principles that we talked about earlier. And then we're going to say, right, for those parameters, how many positrons and how many antiprotons do we predict to be seen at AMS? And then we'll adjust the cross-section until the cross-section predicts significantly more positrons and antiprotons than we actually saw. So then, what does that allow us to do? So these are limits from 2013, the Bergstrom and al paper doing this analysis. So this is looking at annihilation into leptonic channels. So I told you that if you make lots of electrons and muons, it's relatively hard to see in gamma rays, but we can look for the charged particles directly in a cosmic ray experiment. So this is what that bound looks like. So the blue line is for electrons and is for annihilation straight to electrons and positrons. Because that annihilation would produce like a sharp spike in the data, it's relatively easy to exclude. And we can test that in this analysis, they say, for dark matter mass, well, their central line is for dark matter masses up to 200 GeV. But I don't know if you can see it well, but there's kind of a gray band around this. That's their estimated systematic error based in large part on those propagation uncertainties. Okay? So like just uncertainties in the diffusive propagation model. So, you know, if we take one edge of this band and we would say, oh, maybe actually we can only test the, and again, this gray band here is the thermorelic cross section, which I'm just using as a benchmark. then maybe we could say, oh, we can only test the thermorelic cross-section up to like 80 GeV once we take those uncertainties into account.
Just a quick question. Are these one sigma or two sigma continuum things?
I believe these are their 2 sigma limits, so they're 95% confidence limits, I think. You can go back and check the original paper, but I think these are all 95%.
Thank you.
Good question. And so for annihilation into muons, we have this red line, the limit's a bit weaker. That's because there the spectral feature is not as sharp. There's not as sharp a cutoff. You don't get as distinctive a signal. It's not as easy to tell from the background. And then the green is showing the limit for annihilation into taus. There's actually a recent paper that just came out by John and Lyndon that came out last month. And that claims to improve these constraints by like a factor of 2. But I haven't yet had time to dig deeply enough into that paper to see how they're treating the propagation uncertainties, which is always the key question in these analyses. Okay, but broadly speaking, you should think that these kinds of searches can probably probe dark matter up to about 100 GeV, annihilating with a thermorelic cross-section, or heavier dark matter annihilating with a higher cross-section into these lepton heavy channels. But the main uncertainties here are not about the dark matter density. They're about how the charged particles propagate through the galaxy. Okay, so similarly, so for production of antiprotons and heavier hadrons, there's another source of uncertainty, which is just that, like, what is the rate to make them when the quarks hadronize after the dark matter annihilates or decays, and what is the rate to make them when protons in the background, when protons collide with each other with the gas. These production uncertainties can also be significant. But attempting to marginalize over those uncertainties, people have set limits from antiproton observations on annihilation to hadronic channels. And this is what some of these bands look like. This is from a 2018 paper. Again, the width of this band is telling us about the systematic uncertainty from production and propagation cross-sections. And these are for different channels, like green is for BB bar, like what we were looking at before with the dwarf galaxies. And yellow is for like quarks, H is for annihilation of Higgs bosons, and so on. So we could continue like this. But you see the thermorelic cross-section is out here, 2 times 10 to the minus 26 centimeters cubed. So you can say that these constraints are sort of probing multi-hundred GeV dark matter. But again, if you're at the bottom of this system, if you're sort of at the top of this systematic band, maybe they're not really probing the thermorelic cross-section at all within this mass range. Question?
So I guess I'm kind of surprised. What do you think?
I guess I'm kind of surprised that we can set such good limits for these hadronic final states. I mean, when it hadronizes, it's just a mess. I mean,
But it makes a lot of proton, but it can make a lot of antiprotons. I mean, it's also like, I mean, AMS is a fantastic, I mean, AMS02 is a fantastic experiment that has very high sensitivity to these high energy cosmic rays. But yeah, no, when you do the, I mean, again, there are these uncertainties from propagation. You can see, like, I mean, this band is almost an order of magnitude wide in terms of how strong the constraint will be. But yeah, it turns out that 300, so you can do the back of the envelope estimate yourself, like ask if I have 300 GeV dark matter annihilating with a thermorelic cross section, how many antiprotons would I expect to see if I observe for 5 years, whatever, in the neighborhood of the Earth. It's a reasonably large number.
thank you.
For this graph, do you assume some mediator for the process, or like it's an effective model?
So right, so what we're doing here is just saying, let's presume that the final state is a two-body final state with some cross section. Having specified that, that is all you need to know to work out the signal. So with this cross section in our galaxy. So if you had like a very light mediator in the problem, that could give you some velocity dependence in the cross section. That means that when you evaluate the sigma b, you know, strictly what you would be taking is some kind of like average sigma b over our galactic halo, and you might need to do a more careful prediction to account for that. broadly speaking, what you should interpret this as is sigma b at a velocity of about 10 to the minus 3 times c, which is the typical speeds of particles in our galactic halo. More generally, I mean, a general model is likely to give you different branching ratios in 2 different channels. So, you won't annihilate 100% to BB bar. You might annihilate to other channels as well. But again, you can see that across a pretty wide range of channels, the limits are pretty similar. So if your model predicts large branching ratios into any linear combination of these channels, the limits are still going to be in this ballpark. But if you want to do the calculation carefully, what you would do is take your appropriate linear, you would have to sort of redo the analysis that these guys did. You would take your favorite dark matter model, you would work out the spectra, you would work out the branching ratios into all the standard model final states, you would work out the spectrum of antiprotons that's produced, you would propagate that through the galaxy, and you would compare it to the AMSO2 data that I showed on the previous slide. So yeah, but yeah, so basically this is like a basis set. This is showing the constraints on like a basis set of final states. Most dark matter models will give will decay or annihilate into a range of different standard model final states with non-zero branching ratios. But the basis states will be these kinds of states.
Yeah, I think my question is like if you have some cutoff or like in the model or you don't.
So all we need to know for purposes of this question is what standard model particles are produced with what rate. So this can apply to many different kinds of dark matter models. Like there are many different Lagrangians that will give you signals that will show up in this. But the experimentalists present it this way because this is relatively model independent and can then be applied to a lot of different models. So yeah. All you need to know is the rate and what standard model particles are produced. Okay. I want to mention one other type of search for leptonic channels, which is that we've talked about how electric charged particles propagating in magnetic fields produce synchrotron radiation. So that can produce radio signals. Now, these radio signals kind of have twofold systematics. First, they have the systematics associated with the propagation of the charged particles through the galaxy, because it's as those charged particles are propagating that they're making synchrotron. Second, they have systematics associated with the fact that synchrotron radiation depends on the magnetic field. And the magnetic field through the galaxy is often not that well known. That said, there have been some pretty credible attempts recently to try to look at regions which are large enough and where the B field is well known enough that these systematics are not huge. And they can claim very strong limits, like up to hundreds of G, up to the thermorelic cross section of hundreds of GeV. So that's comparable to these limits from AMS with like reasonably optimistic predictions about the propagation conditions. So this is something to be aware of as well. I'm not sure it's enough to completely convince me that like dark matter models with a thermorelic cross section at 100 G, 200 GeV are ruled out, but you should be aware of this. Okay, so these last 2 slides, if you have a dark matter model in the sort of 10 to several hundred GeV range, annihilating into visible standard model particles, these are likely to be the strongest bounds on your model from indirect detection. Okay. I will say, so there's one exception to this, which is if your model has a strong gamma ray Lion signal, then then everything I showed you before is for annihilation to hadronic final states or leptonic final states. But there's that other category we talked about the first day, which is what if you have 2 dark matter particles annihilating straight to 2 photons or to a photon into some other particle. Then, because we have a spectral line, that's a very low background search. Now, if you're doing a very low background search and you're looking for a signal that you're not sure it's going to be there, but if you found it, it would be spectacular, then it can be advantageous to look at regions like the galactic center, which have a very high J factor. Again, setting constraints on this, the uncertainties will be large, and you will need to think about different possibilities for the dark matter profile, but you increase your chance of seeing a signal. So for this reason, the gamma ray telescopes also look towards the galactic center and set upper limits on the signal from the galactic center. So there are stringent limits both from Fermi-Lat and Hess. There are also limits on continuum emission from the galactic center. It's just that there, I think the Fermi dwarf constraints are more robust. So for these line limits, these are examples from analysis by Hess in 2018, so which is one of the ground-based gamma ray telescopes. These blue and these red lines are showing the cross-section that they would have sensitivity to with their gamma ray line search in the galactic center. assuming an ionosphere profile in one case and an NFW profile in the other case. And then these triangles down here are the corresponding line sensitivities from Fermi. Okay, so same kind of exercise here. We imagine saying, so there's an example exercise like this in the notes. We say we've got a photon line at some energy. Given a cross section, we can predict how many photons we would see from that photon line at the Earth. We can look at the known backgrounds in the area, figure out how large the cross section would have to be for that to be excluded. And so you get a set of limits like this. So you can see, so the scale on this is 1 TeV. So the thermorelic cross section is up here. So these limits are way, way stronger than thermorelic, but we do not expect most thermorelics to be annihilating 100% into gamma gamma. So we expect the branching ratio to be small. Yeah, question?
Does the dark matter have to be milli-charged for this to be a viable production
No.
mechanism?
Okay. By production mechanism, do you mean like to produce the dark matter, or do you mean for there to be a viable signal?
Sorry, I meant for there to be a viable signal.
No, it does not need to be milli-charged. Let me show you an example.
Please.
So my favorite, Tracy's favorite supersymmetric dark matter example, we know dark matter. So yeah, you've talked about supersymmetry with Jonathan Bank. By we know dark matter, we mean fermionic dark matter that transforms under the standard model SU2 gauge group. It's in the triplet representation. And in particular, that means it interacts with the weak gauge bosons. We've talked about this a bit before. So and it appears in SUSY models as the W superpartner, but more generally, even if SUSY doesn't exist, there's nothing wrong with the idea of having a heavy fermion that is charged under the standard model SU2 gauge group. The general class of these models is sometimes called minimal dark matter, and Marco wrote one of the seminal papers on it sometime back, or the seminal paper on it called minimal dark matter. So the naive expectation, so as we talked about before, this is forbidden at tree level because this is a neutral particle, it doesn't couple directly with the photon. So this process doesn't exist. But it can occur at one loop because the Wiener has a slightly heavier trigeno partner, so we can get diagrams that look like this. A naive expectation, sorry, it's a question here.
Sorry, I didn't a bit. So I guess I'm wondering if we have any kind of upcoming sensitivity or statistics to do this same line search for something like neutrinos or something.
Neutrino lines, so I think yes in principle, but I don't think we've seen any neutrinos that we're convinced are from the galaxy. So like, I mean, if you're at the limit where your signal is 0, then questions about like, you know, is there a sharp line in this bin, but become somewhat trivial. Like you can just do a counting experiment. But yeah, I mean, you could. I also don't remember what Ice-Cube's energy resolution is. I'm not sure it's great. Mind you, Hess's energy resolution is also not great, and you know they can still do a line search. But yeah, I think with the neutrinos, we're just at the limit where we don't really have enough neutrinos to be able to, well, okay. I mean, Ice-Cube has detected high energy neutrinos that we think are not coming from the atmosphere. So you could take that neutrino spectrum and ask if there is evidence of sharp features in it. But my recollection is the total number of neutrinos they've seen is like in the tens, which means it's going to be hard to resolve much of a line. So yeah. So I think that you're in a problem where the statistics are low enough that your problem is not you have a large background and you're trying to find a little bump on top of it. The problem is just that you just don't have that many events. Yeah. But like, yes, in principle, given enough neutrino events, you could absolutely look for a neutrino line.
Is this something that seems, I don't know, upcoming, or are we way out there?
I think you need to see more neutrinos first before that kind of analysis. So yeah, I'm gonna punt on that question and point you to some white papers about future searches with Ice-Cube and with future neutrino experiments.
Okay.
But I think that, you know, I mean, yeah, like I think for the moment, it's also true that, I mean, you can get a neutrino line, but probably the neutrino signal that you would expect to see first if there's, well, I mean, okay, you could go 100% to neutrino, anti-neutrino, that would give you a line. You can, so, I mean, you could certainly like, so I guess I'll say nothing. Certainly all the neutrino experiments do set upper limits on the annihilation cross-section to neutrino, anti-neutrino. So that, I mean, that is a line search. But And they also set limits to other channels where your annihilation is to hadronic states that decay and make neutrinos. So yeah, I mean, so right. So like, I mean, at some level we are already doing the line search with neutrinos, but it's not, and it would be a background free search, but just beating down the backgrounds is less of a concern for the neutrinos than it is for gamma rays, because I mean, I think, yeah, like I said, my recollection is the high energy neutrinos that Ice5 has seen are like, 20 or 30. I don't know if someone in the room knows the answer.
Yeah, I mean, it's less than 100.
Yeah. Like for comparison, Fermi's detected some hundreds of millions of photons during its time up there. So we're just in a really different regime. But yeah, like but to directly answer your question, all the neutrino experiments publish constraints on annihilation or decay to neutrino, anti-neutrino. So that would be a spectral line.
Yeah. Actually,
Yeah.
there's a paper published in 2013. I forget who wrote it, but they did a door toroidal search. And those are, at least for the moment, Ice5 store toroidal limits with into neutrinos, or with chi into neutrinos. I'm actually going to be doing that analysis again.
Oh,
so-
excellent. Excellent. Great.
That I don't know how long that paper will take, but that's, I guess I'm the guy that put in to do that next.
Awesome. Great. Right. So the point I want to make about the Wino is that, so focusing on this, so you might look at this and say, okay, so this is going to be small, this is going to be loop suppressed, this is going to, be down by some factor of alpha. But actually for Winos, this expectation breaks down once the dark matter mass is much heavier than the W mass because of the Sommerfeld effect behavior that we talked about earlier. The W's effectively give a long-range attractive interaction between dark matter particles. And what having a long-range attraction means is that these W exchanges prior to the annihilation of the particle are not, the diagrams that dominate are the ones that have a very large number of these W exchanges. Because these particles are propagating in a long-range potential where the W's can just go back and forth pretty freely. As a consequence of that, you find that the diagrams that dominate are the ones with an infinite number of exchanges. The only difference between the diagram that ends with a chi-naught and thus can't go to photons, and the diagram that ends with a chi plus and chi minus and thus can go directly into photons is typically an order 1 number, because it's just the difference of one more run in the ladder. You're taking the limit of ladders that have a lot of runs. So the consequence here is that for the Wino case, not only is this gamma-gamma line open, but it has a cross-section that is more like a Sommerfeld enhanced tree level cross-section than a loop level cross-section. So, and that's due to the presence of light mediators plus charged particles that are not much heavier, plus charged partners that are not much heavier than the dark matter. So a long-range potential can not just affect the overall strength of a signal, it can also affect the relative shapeability of different channels. Things that you think are loop suppressed without the long-range potential may effectively become tree level, plus the enhancement in the presence of the loop potential. So you can look at this and say, okay, great. So I should be able to set limits on Winos by looking at the galactic center in gamma rays. I will say there's a bit of extra theoretical subtlety to this, to which I'm not going to go into detail. You also get large log corrections coming from box diagrams when you try to calculate this cross-section and you need to resum those large logs, and I and other people have done a fair bit of work on that over the years. But it's been done, and when you do it carefully, what you find is that, so this upper plot is showing the limits on the cross-section for the line as a function of the dark matter mass. So this is for an ionosphere profile. This is with a Hess-like observation. This is the bound, and the green and yellow lines are the expected expected range of the possible bounds. So this is a sensitivity. Hang on, sorry. I'm just reminding this. Sorry. This green band is actually the sensitivity for a future experiment. Mess that up slightly. The current Hess sensitivity is this blue line. And the gray line is a theoretical prediction for what the signal should be. And the blue line and this blue vertical line here is telling you at what mass the Wino would have the right mass to be 100% of the dark matter. So what you see is short line is for an ionosphere profile, this gray line at the thermal Wino mass is way above the sensitivity line by more than an order of magnitude. Yeah.
Why does the cross section have that shape?
Why does it have the oscillatory shape? These peaks are the resonances in the Sommerfeld enhancement. There was when there's a near zero energy bound state in the system, and thus you get a 1/v squared scaling in the cross section, part of the evolution. So yeah.
Yeah.
These peaks are a signature of the Sommerfeld enhancement is important in the system. So you might say, okay, but that was the Inasto profile. I told you there was a ton of uncertainty in the galactic center observations. So how do things change when you give the Inasto profile a core? And what we found essentially was that at present, in order for the WINO to not be excluded, you need there to be a core of about 2 kiloparsecs radius towards the galactic center. This appears to be not expected from simulations, but maybe not totally ruled out. If we still don't see it in CTA, then you would need, which is the upcoming future gamma ray experiment, then you would need the core size to be basically out to the position of the Earth to not exclude the WINO, which we think is very unlikely from simulations. So while there are large uncertainties on the galactic center, you can express it like this. This is sort of like a joint constraint on can the WINO be the dark matter and how flat is the dark matter density profile towards the inner galaxy. You can also, those antiproton constraints that I showed you earlier that were constraining thermal relic cross sections up to a few hundred GeV, you can also apply these to the WINO annihilating in a way that produces antiprotons. And you similarly find there that it looks pretty excluded, although maybe not completely so given the uncertainties on the propagation. But yeah, in both antiprotons and in this gamma ray channel, which have pretty different systematics, it looks fairly excluded. Yeah.
Do you have a predicts on the mass of the WINO?
Good. So if the WINO is heavier than this thermal value, then it doesn't annihilate well enough to be depleted in the early universe that in a way that gets at the correct abundance. So that means that either you need to modify the cosmology so that its abundance gets diluted. You need it to be like not just a pure WINO, but to have some other annihilation channel so that you can get rid of it. Or you need some kind of like non-thermal production and depletion mechanism. So if you do that, you can have much heavier WINOs or WINO like dark matter, but for like just the baseline pure WINO in the completely bog standard cosmology, this blue, I mean, so we showed the results up to higher masses just because you can modify the models in that way. But in the baseline standard cosmology, at higher mass than this, you'll get too much dark matter. So, baseline point here is just, well, there's two things. Heavy electroweakly interacting DM can be not ruled out by colliders and direct detection, but still have very interesting and striking signals in indirect detection. And occasionally line limits are actually the strongest bounds that you have. So another related example of that is Higgsino dark matter. So Higgsino dark matter is just fermionic dark matter that transforms as a doublet of the standard model SU2. It appears in supersymmetric models as the Higgs superpartner, and it gets the correct relic density for dark matter masses around 1 TeV. The Higgsino is really hard to exclude because this is a forecast for a future experiment, not the current bound. The current observations none of the current indirect observations constrain the thermal Higgsino. No current for the direct detection cross section is below the neutrino floor. The current limit from collider physics is nowhere close to the thermal value. Again, this case is somewhat theoretically subtle. You need to do a fairly careful effective field theory analysis, but there has been at least some progress towards that in this work by Beneke et al. So this is not something where I'm going to tell you about a constraint. This is where I'm just going to tell you that people sometimes say the WIMPs are dead. But Higgsino dark matter, I mean, this is a really classic WIMP that interacts through the weak gauge bosons of the standard model. It's completely predictive. It gets the right relic density for a mass of about 1 TeV, and is completely undetectable by all the searches we are currently doing. But in next generation searches, we may be able to get it with lines in CTA, or we may be able to get it at future pointers.
That answers my question.
That was your question about how do we get it in the future? Yeah. So yeah. But yeah, one of the reasons that I roll my eyes a little when people say WIMPs are totally dead, it's like we haven't even killed the Higgsino. This is like the, one of the simplest possible classic WIMP models. So, okay, so we can keep pushing these annihilation bounds up to even heavier dark matter masses. So if we trust Hess observations of the inner galaxy and we believe that the density profile towards the center is NFW or Inasto, which you maybe should not believe, then you can set limits on the thermorelic cross-section up to around a mass of around 1 TeV. So that's this green line here. This is showing the Hess limit. So this is Hess observations of the galactic center, assuming, I think they assumed Dynastro, but I would have to double check which one it is. So you see at low energies, this is below Hess's energy threshold. You can't really see anything. And at high masses, they lose statistics, but they can constrain sort of thermorelic-ish cross-sections around 1 TeV. That said, if there's a flat density core, this green curve will move up. In future experiments doing the same kind of analysis, the limits will get much better. This red line is a forecast sensitivity from CTA, which is the next gen planned big gamma ray big gamma ray ground-based telescope. And this gray line is a possibly even more optimistic forecast from the Southern Wide-Field Gamma Ray Observatory, which is a proposed experiment. So, you know, not planned, not funded, proposed as a possibility for the future. So the claim is that by looking at the inner galaxy, again, if we have an NFW or an Astro-like profile, then we would potentially be able to test the thermorelic cross-section for dark matter masses up to around 100 TeV, which gets you close to the unitarity bound that Josh might have talked about, that once you go to higher masses than this, it's actually somewhat difficult to get the right abundance just through annihilation. We can push to even, if we don't care about the thermorelic cross-section, we can push up to even higher masses. This plot is from an analysis by Miraze et al. In 2012, and I guess you can't see the end of the x-axis here, but I think this goes up to 10 to the 10 GeV. Very good. Okay, 10 to the 10 GeV. So right. So this goes up to 10 to the 10 GeV. So this is very heavy. So in order to do this analysis, what they need to look for is, as these particles are injected into the universe, what cascade of secondary particles do they produce as they propagate to lower energies? Yeah.
I guess I should.
I mean, I feel like I guess I should know this, but I mean, eventually, as your dark matter gets too heavy, it's not smooth enough to give you a halo and to reproduce.
That's true, but we're a long way away from that limit.
And
So
roughly where might that be?
well, so as an example of what's not excluded by that limit, primordial black holes can be 10 to the 23 grams and still be totally legitimate as a dark matter candidate. Like and that's not just getting structure formation right, that's like not violating constraints from gravitational lensing and a bunch of different contexts. The smallest dark matter halos that we directly observe, like the bottom of the matter power spectrum, are I think around 10 to the 7 solar masses. So provided that your individual dark, well, I mean, again, you heard Annika, you know, dark matter particle masses in simulations are often 10 to the 3 or 10 to the 4 solar masses. And those agree with observations. So if your individual dark matter particles in reality were up to 10 to the 3 or 10 to the 4 solar masses, you would still get structure formation for.
And I mean, but can you recreate galactic rotation curves?
Yeah.
Really?
Simulations get galactic rotation curves right with particles of 10 to the 3 or 10 to the 4 solar masses. So yeah. So yeah, thinking about 10 to the 10 GeV, it's you have many orders of magnitude of leeway. So
If you're looking at annihilations and decays, does that unitarity bound get pushed up?
good. Okay, so what this unitarity bound is saying, right? Good. Okay, so this is, you could certainly, right? So right, good. So this is saying this is a unitarity bound on S-wave annihilation. So provided that you only have S-wave annihilation contributing, while these bounds do exist at higher masses, they're somewhat irrelevant because they would require unitarity violation in the theory. But suddenly you can have, there's not a significant unitarity bound on the decays. So you can have decaying dark matter that is much heavier, and these same kinds of constraints can be repurposed into constraints on decaying dark matter at high masses, and I'll show you that shortly. Okay. Yeah.
Sorry, my question, and maybe you already answered that, but all these constraints in general assume that dark matter annihilates through only one channel, right? So if you take into account the branching ratios, this constraint will be weaker.
So as I said, the way that as I said earlier, the way that these constraints are typically presented is with these fixed two-body final states. If you have so if you have finite branching ratio, if you have branching ratios into different final states, and you want a precise constraint, what you usually need to do is work out the spectrum of particles, go back to the original data, and recompute the constraint. That said, for many channels, the signal in charged particles or in gamma rays is pretty similar. Like anything that hadronizes is going to be neutral ions and charged ions, and the spectrum is just not super different from state to state. So do a pretty good approximation, something that is a third into B quarks, a third into charm quarks, a third into light quarks. The limits for all those three, if I looked for the limits for 100% into B quarks, 100% into charm quarks, 100% into light quarks, the limits are all going to be quite similar. And the limit for the a third case is going to be quite similar to any of the things that enter into the average. But if you have something where, let's suppose I have a 50% branching ratio into electrons and a 50% branching ratio into B quarks, then I mean I can be conservative and just say, okay, well, maybe Fermi will constrain the branching ratio into B quarks, and so I'll apply the Fermi cross-section bound to my cross-section divided by 2, and AMS will constrain my branching ratio into electrons, so I'll apply the AMS bound to my overall cross-section divided by 2. So you can do that, and that's conservative. But if you want a constraint that's as powerful as you can get it, you want to compute the full the full spectrum of particles in both cases and compare it to the original data that's going into these things. Okay, so actually you just asked about decaying dark matter. So here's what the limits look like for decaying dark matter of 1+ masses. So this is an analysis from Cohen et al. In 2016. So this red line is a constraint from Fermi. So you'll note this mass scale starts at like tens of GeV and goes up to 10 to the 10 GeV again. These red lines are limits from Fermi. The reason why Fermi can set interesting limits on 10 to the 6 GeV dark matter, even though it's only really seeing particles up to a TeV, is again because of these secondary cascade effects. The 10 to the 6 GeV particles will produce secondaries that are lower energy, and Fermi can see the secondaries. This red dotted line is what Ice5 takes over in the constraints. So at higher masses, so this is for annihilation to B quarks. If we were looking at annihilation straight to neutrinos, this would be Ice5 all the way. But this is for annihilation to a hadronic channel. Ice5, because it has sensitivity at higher energies, takes over from Fermi once we get above about the PeV scale. And this green and blue regions, we're trying to actually explain Ice5 high energy events by decays of heavy dark matter. So you can see that across this whole high energy range, and at lower energies, we'll see this continues down to about the keV scale. We're constraining lifetimes around 10 to the 27 to 10 to the 28 seconds, which is a couple of orders of magnitude better than our sort of cosmological backup constraints. It's also possible to push even beyond this point. So this lower plot starts at 10 to the 10 GeV and then goes up in mass from there to 10 to the 17 GeV. It's possible to set some limits on decaying dark matter at those scales by the non-observation of very high energy cosmic rays and EEV photons. And I'm just there are a couple of white papers for the SNOMAS planning process. I've given you the references here. And so they have some discussion about what we might be able to do with these probes. So indirect detection really does give us limits on extremely heavy dark matter, pretty much all the way up to the Planck scale. Whether those limits are useful for your particular model, is another question. But we can see the annihilational decay products up to very high energies. Okay, if we think about so I've talked a lot so far about limits for classic WIMPs and heavier GeV, 100 GeV, TeV, and one justification for that is that at the GeV scale and lower, the CMB bounds that I talked about earlier are pretty powerful and essentially rule out the thermorelic cross section. But you can still ask, what are the other bounds in this region? We might be interested in cross sections that are much lower than the S-wave thermorelic cross section, like P-wave suppressed cross sections. Can we test that at low masses? Can we test cases where the dark matter is mostly asymmetric? So as I mentioned, the cosmological constraints are strong here, but there are also complementary limits from Voyager, as we've talked about before, and from X-ray and gamma ray observations. So these are some nice plots for these bounds of the dark matter annihilating to charged pions, or to muons, or to electrons. Again, from one of Marco's recent papers. This dotted line down here is showing the CMB wave bounds, and you can see that on this plot they're stronger than everything else. But these other channels can be much stronger if the annihilation is P wave suppressed, because the dark matter is going pretty slowly at the time of the CMB epoch, and it can be going faster in the present day galaxy. So that makes the V-squared suppression less severe. Here's Voyager, heroic 1970s Voyager, and you see like it actually does better than a lot of the other constraints, at least for annihilation into electrons. And then these other limits are from X-ray and gamma ray telescopes observing the halo of our Milky Way galaxy. For decays, you can, and okay, this is a similar limit for annihilation straight into photons, coming from the CMB and from integral and from the New Star telescope. And there are other limits like this. This is just one example that I'm familiar with because I was a co-author on this paper last year. Again, these are way subthermal cross sections. So the question is, sort of, we're thinking now about probing P wave cross sections or other cases where the annihilation is suppressed at late times or where we're not looking at a thermal relic at all. For decay, we can do the same kinds of exercises. X-ray and gamma ray telescopes can again set constraints for anything that produces photons. The decay lifetimes tend to be around 10 to the 27 to 10 to the 28 seconds. These are limits from COMPTEL, which is a gamma ray telescope, Integral, which is a soft gamma ray telescope, and USAR, which is an X-ray telescope. For leptonic channels, the limits can be slightly weaker, down to around 10 to the 25 to 10 to the 26 seconds. This is a plot from a recent paper that Wenzer and I wrote with our collaborators Hongwen Liu and Greg Ridgway. And so again, this is decay lifetime, so everything below this lifetime is ruled out. The black line is the CMB bounds we looked at earlier. These blue and red and orange lines are limits from the Lyman alpha forest. The differences correspond to systematic uncertainties. And this dotted line is Voyager defeating us in the 10 to 100 MeV mass range. And then once you go up to 1 GeV and higher, then Fermi and other higher energy gamma ray telescopes take over.
Just out of curiosity, is Voyager expected to keep taking data indefinitely until it breaks down?
I don't know what the expected lifetime of its cosmic ray spectrometer or communication mechanisms are, but as far as I know, yes.
I think I remember there is a plutonium battery which is dying slowly, like
Okay.
in 10 years it will be gone.
Oh,
Otherwise,
left out.
But got to get lots of observations of interstellar cosmic rays before then.
I think it's a naive question, but can you extract any limits from observation of optical telescopes like Hubble and James Webb?
It's a good question. So I have mostly focused in these talks on KEV and heavier dark matter. And for that case, I don't think while you could potentially get a signal in optical telescopes, I haven't actually seen the limits, but I would guess that they're not very strong because there's kind of a mismatch between the energy range you're looking at and the energy range to which the particles are injected, and there's a lot of optical background. What optical telescopes are really powerful for is, mapping out the distribution of stars in the universe and thus allowing us to map out the distribution of dark matter. But for pure indirect detection constraints, I think from these heavier dark matter models, you probably don't expect to get a ton of power in the optical channel compared to the background there. That's it. I haven't done the calculation in detail, so maybe there's something to be done there. So you might say, okay, but what if I've got like 10 EV dark matter? Thing is, once you're talking about like 10 EV, 1 EV lighter dark matter, it needs to be pretty decoupled from the standard model in order to not have been relativistic at important times in the universe's history. So yeah, I mean, and I think you can look at like freezing dark matter, but I think the freezing dark matter models that I've seen are excluded by cosmological bounds when you go that way. So, I mean, yes, in principle, you could do searches in optical. The question is just, are there interesting dark matter models that populate that space? But I mean, in principle, you could. But I'm not going to be showing any of them in this talk because I'm mostly looking at the images. Okay. So yeah, this is just my aside about Voyager, but we've already had this discussion. And I just wanted to mention that this MEV, so if you look at the sensitivity of our telescopes as a function of energy, this is like the continuum set. This is this is just like a sensitivity measurement. How bright does a signal have to be before we can see it? Down in the X-rays, we have great sensitivity. Up in the GeV plus gamma rays, Fermi-Lat is great. This black line is a future planned experiment. So the current status is every line except black line. So we have kind of a gap in sensitivity just in the MEV to GeV band. It's not a total gap. We do have telescopes there. They can see stuff. But because of this, there's been quite a lot of interest by experimentalists in building telescopes that can do significantly better in this MEV to GeV band. These are the Amigo and Compare proposals, and these will hopefully happen over the time scale of like the next 10 years. So this is just an area where the limits could get quite a lot better in the not impossibly distant future. And this paper by Coogan et al. Was looking at one example of the case where dark matter is primordial black holes, and those primordial black holes are decaying away, and asking what limits you can put on the dark matter mass with current telescopes and with planned future telescopes. And the current bound is this black line shaded in gray, corresponding to a minimum mass for the black holes of about 10 to the 17 grams. And at least this paper, which may be a little overly optimistic, but maybe because I've seen other papers that don't get quite as big a reach improvement as this. But this work suggests that we may be able to get like an order of magnitude improvement in primordial black hole mass reach with these future telescopes. So that's again just something to keep an eye on. Sorry, this is primordial black holes. So these mass scales are masses in grams.
Okay.
Yeah, thank you for asking. Yeah. I think that's not the projector's fault. That's that I accidentally snipped off grams when copying the plot. Yes. The rest on this plot is just propaganda for the MEV to GeV band generally, which I think you're probably convinced of after listening to Tom's talks. Okay, so with 15 minutes to go, I want to talk. Sorry, thanks for all the good questions. This is awesome. I want to talk about anomalies. Okay, so I'm going to give you the super quick run through of anomalies, and then tomorrow in the discussion session we can talk about this in a bit more depth. Okay. So for this reason, I may ask you to hold questions until the discussion session tomorrow. So do note them down because I'm sure they'll be awesome. But I want to give you the sort of brief overview picture tonight, and then tomorrow we can talk about it. Ask me more about anyone that's interested. Okay. Okay, so this is my one slide summary of some excesses and anomalies in indirect detection. I may well have missed some. So most of the anomalies that I'm going to be talking about are potential signatures of annihilation and decay. One of them is actually I said way back at the start of the first lecture that indirect detection could also include scattering between dark matter and baryons happening out in the universe. One of the anomalies that I want to mention could potentially be a signal of that kind of dark matter baryon scattering. So other ones that I want to mention. AMSO2, as we said, it has this bump in high energy positrons. If you want to explain this with annihilating or decaying dark matter, then you need dark matter that is around the TeV scale. And if it's annihilating, it has to have a large cross section, much larger than thermal. So that points you towards models where the dark matter, maybe experiences some fold enhancement or a resonance or some other, leg time enhancement to annihilation. So the leading alternative candidate is that we're looking at positrons streaming off nearby pulsars. AMSO2 has quite a lot of these excesses. The next possible annihilation decay signal is that AMSO2 appears to see a modestly significant little bump in the antiproton spectrum at energies between around 10 to 20 GeV. This is much less visually noticeable on the antiproton spectrum than the positron bump is on the positron spectrum. But it's easier to explain from a dark matter perspective. You only need sort of order 80 GeV dark matter with a thermal Rayleigh cross-section. However, as I'll tell you, there are serious questions about whether this is actually statistically significant. AMSO2 has claimed in unpublished work to see 8 anti-helium events. This is extremely surprising from a perspective that includes dark matter or does not include dark matter. The forecast signal for how many anti-helium events you should see from both signal and background is 0. It is pretty firmly 0. But there's been some recent theoretical work that I want to mention to you that suggests maybe you could make this work with dark matter annihilation. Another possibility is that there are some kinds of antimatter stars or antimatter clouds relatively close to the Earth that are somehow producing this antihelium. Another possibility is that it's some kind of instrumental issue. going on at a different, so these are all sort of in the, these are all at relatively high energies and sort of tens to hundreds of GeV band. At much lower energies, there is an apparent 3.5 keV X-ray line detected in a wide range of systems. The simplest dark matter explanation is that this is a 7 keV decaying sterile neutrino that's decaying to a photon and a neutrino, and we're seeing the photon. There are the possible backgrounds for this are mostly atomic reactions that give rise to lions or forests of lions in this energy range. There have been, again, challenges to the statistical significance of this excess, and it may be excluded by non-observation of counterparts in various halos. And the last one is the galactic center excess, seen in Fermi gamma rays, which is a glow of roughly GeV scale gamma rays coming from the region around the galactic center, which was discovered by Goodenough and Hooper in 2009. This is, Lisa's a good friend, but definitely good enough. And yeah, so yeah, it was Lisa Goodenough and Dan Hooper found when Lisa was just a grad student. We were both grad students at the time, and yeah, this was pretty exciting. And so this is also a case like this, and the positron excess are both the most statistically significant by far of these excesses. They're both, these are not statistical fluctuations, but the galactic center excess may also be telling us about pulsars rather than dark matter. And the last one I mentioned was, yes, the edges. So this is, I mentioned earlier that there was a claimed observation of the primordial 21 centimeter signal, which could potentially be explained if the gas was really cold in the early universe, and that could maybe be explained by dark matter baryon scattering. So that's my anomaly list. Okay, let's say a little bit more about some of these. So this is a positron excess. This blue region is showing the counterpart spectrum of the electrons. This red region is showing the spectrum of the positrons. Now, we argued earlier that generally secondary particles should have a softer spectrum than primary particles. So if the electrons are primary and the positrons are secondary, are coming from proton collisions with the gas, this is not what you would naively expect to see. Positrons go up much faster than the electrons at high energies. Note, however, that the scales on the two sides of this plot are different. Like there are fewer positrons than electrons. So for example, it's not excluded that the electrons would have a subcomponent that is rising as fast as this positron component. It would just be a subdominant component compared to most of the electrons. So the fact that this spectrum goes up is really statistically significant, as you could just estimate from the error bars. And it also appears, although not as high significance, to be falling again at higher energies, which is interesting. It suggests some kind of cutoff in whatever the underlying source is. So it looks extremely likely that AMSO2 has discovered some source of primary positrons in our galaxy. The question is what that is. If you try to explain it with dark matter, the easiest thing to do is say TeV scale dark matter annihilating or decaying in a way that mostly makes leptons. We don't see a bump like this in antiprotons, so that's where the dominantly into leptons comes from. If we're looking at annihilation, that requires a rate several orders of magnitude above the thermal rate. So to make that work, you can think about models with Sommerfeld enhancement or similar. However, there are some serious challenges to the dark matter interpretation. Basically, that if we were pumping this many positrons into the galaxy, we would have expected to see some other signals. As those positrons move through the galaxy, they should be making gamma rays when they scatter on the radiation field. And in the early universe, if we dump these many positrons into the early universe, they should have ionized the gas, and we should have seen it in the CMB. So for those reasons, this interpretation, but the annihilation interpretation appears nominally ruled out both by the CMB searches and by gamma ray searches. You can maybe get around this. This paper has an example of a possible way to get around this, but it takes some maybe implausible model building. Like this paper involves both some extra particle physics ingredients and requiring that there's a really dense clump of dark matter at the center of the galaxy, like 200 times larger than you would expect from the NFW cusp. So again, take a read of this paper if you want to see an example. This may not be totally ruled out, but we would have naively expected to see some counterpart signals that we have not yet seen if this was coming from dark matter annihilation. Dark matter decay is in better shape. It's not in conflict with the CMB if this is coming from dark matter decay. But again, there are constraints from galaxy clusters in the extragalactic gamma ray background. This is an example from a paper by Blanco and Hooper in 2019, looking at these blue regions or limits on the dark matter decay lifetime from the extragalactic background. And these red lines are the lifetime that you would actually need to explain AMS. And you can see that except at very low energies, where they wouldn't explain the whole spectrum of the positron bump, it's in conflict. And this is just, again, the CMB constraints recast. These this red point should be compared to these red constraint lines, these gray regions should be compared to these other constraint lines. And you can see that in general, like you just need an annihilation cross-section that is larger than would be ruled out by the CMB bounds. So what do we think it actually is? So in 2017, the Hawke Gamma Ray Telescope was looking at nearby pulsars, and they discovered that there appear to be halos of TeV gamma ray emission around them. This is a bit surprising because if we put in those estimates for the diffusion coefficient that I told you about earlier, and you asked how far TeV electrons or positrons would diffuse from the pulsars, they would go far enough that these halos would be expected to be like 40 degrees wide on the sky, in which case Hawke could not have detected them. They would have been smeared out too much. In fact, they're only about 2 degrees wide. So this could mean a few different things, but the hypothesis now seems to be that the pulsars are producing TeV electrons and positrons, but diffusion around the pulsars is impeded. So we have some inhomogeneous diffusion. But what this does imply, if true, is that a pretty large fraction of the spin down power of the pulsars is going into electrons and positrons, and those electrons and positrons are above the TeV scale in energy, which means that after they propagate to Earth, they would still potentially have enough energy to explain the AMSO2 positron excess. So this is an example model from this paper by Hooper et al. In 2018. So this blue line is a model based on the sum of local pulsars trying to explain the AMSO2 data points, which are shown in red. Now, this is a fit to the data. This was not like an a priori prediction before they saw the AMSO2 data. There are various parameters that you can tune about like how the impeded diffusion zone works. But it looks at least pretty plausible. I mean, we now know that local pulsars are making positrons that have enough energy and abundance to potentially explain the excess. So my personal view is that this is the most likely explanation at this point. But again, so that's what I wanted to say about the positron excess. So excess number 2, AMSO2 excess number 2 is this apparent low energy antiproton bump. So you might look at the antiproton spectrum and say, what bump are you talking about, Tracy? So so like this is the antiproton spectrum, one of the discovery papers. So these 2 papers in 2017 identified this potential excess, and red is the size of the claimed bump. Okay, so this is why you can't see it on the log plot, because it's a 10% effect. But it does improve the residuals to include the dark matter component by a nominal local significance of about 4 sigma. The original papers claimed about 4 sigma significance. And it corresponds to a mass scale of about 10 to the 20 GeV in the antiprotons. And so then if you look at what the limit is on the cross-section for dark matter annihilating to antiprotons, this is from Corco et al., this is what they found. Previously, I just showed you the results at higher dark matter masses, this side of the plot, but they see this big upturn in their constraints corresponding to a dark matter mass around 50 to 100 GeV. And that's because dark matter in that mass range annihilating, this is an example, to B quarks could potentially explain this kind of bump. It doesn't have to be B quarks, like other hadronic channels will work fine. This is just an example. Okay, so the cross-section you need, unlike the positron excess, you don't need to do anything special with the cross-section. The cross-section you need is bang on the thermal relic line. It's about 2 times 10 to the minus 26 centimeters cubed per second. The dark matter mass you need is between 40 and 130 GeV. And so, that's maybe interesting. This also aligns pretty well with the parameter space of the galactic center excess. However, this is not highly significant. It could just be a statistical fluctuation. And in particular, there's been a large amount of work over the last few years by several groups noting that these error bars in AMSO2 do not look consistent with statistical errors that are uncorrelated from bin to bin. So there are bin to bin correlations. So these papers by Burat et al. And Corco et al. Each said, okay, let's try to cook up some kind of sensible estimated covariance matrix for how the errors in different energy bins might correlate with each other. And then say, okay, using our guesstimate for what the covariance matrix would look like, if we use that, how would that change the significance of this excess? Burat et al. Found that when they did this, the significance of the excess went down to less than 1 sigma. Corco et al. Found that when they did this, the significance of the excess went up to over 5 sigma. What I took from these 2 papers was, wow, we really do not know what the actual significance of this excess is. and it will be hard to understand, to know what it is without a better understanding of the structure of the errors and the correlations between the errors in AMSO2 data. This Heisig et al. Paper found similar results to Boudal, that it could be explained purely just by uncertainties in the production and propagation cross sections and by correlations between the errors. And they have some like interesting examples where they show that they focused on the systematic uncertainties in how the cosmic rays get absorbed in the AMSO2 detector, which is another source of systematic error that I haven't talked about. They also show some interesting examples where they show that if you include only some but not all of the systematics, then you can get an effect like what Quirk et al. Saw, where the significance actually goes up. So yeah, so this is, I mean, it's an interesting signal, maybe worth keeping an eye on, but I think these papers make the case fairly strongly that it would probably be premature to treat this as like really a 4 sigma detection of new pesticide. Yeah. Okay, so you might ask the question, and we're gonna have to wrap up pretty soon. So if you ask, where can we go next for positrons and antiprotons, some of this we've talked about already. One possible diagnostic for the positrons at least is the anisotropy in the arrival direction. If it's really coming from 1 or 2 nearby pulsars, maybe you would expect to be able to see an anisotropic signal. So this is when I was saying earlier that AMSO2 was going to find it hard to see sort of 1% anisotropy. That's part of what this plot is showing. So this is the expected anisotropy for signal for positrons coming solely from Gaminga, which is one of the nearby pulsars, or solely from Monogem, which is another one. And you can see, so as I said, the expected anisotropy levels from Monogem are below 1%, and from Gaminga are actually below 0.1%, which is worse than I expected. This paper by Linden et al. In 2014, though, suggested that CTA, so the upcoming ground-based gamma ray experiment with long observations of its cosmic ray data, could potentially say something about the anisotropy of these signals. So maybe we can do something with anisotropy, but it's pretty hard just because the magnetic fields really do scramble the arrival directions pretty comprehensively. For antiprotons, as I said, there may still be work to do just on the theory analysis side, trying to understand like what are the uncertainties in how cosmic rays hit the detector? What are the uncertainties in how antiprotons get produced in collisions? And how do we think these errors should be correlated? But there is an independent possibility for trying to search for this kind of thing, which is that the GAPS experiment, which is expected to fly in the next few years, although I don't know exactly when because the whole schedule has been delayed due to COVID. So there's a nice report on GAPS and searches. What GAPS is going to do is try to look for anti-deuterons. So this should be one of those zero background searches that we've talked about. And if you say, okay, if you had a signal large enough to make this number of antiprotons in AMSO2, would you be able to see it in GAPS? It's very plausible that you would be able to see a counterpart signal. It's not guaranteed, unfortunately. There's not like a no-go theorem that says if you see nothing in GAPS, then you can completely rule out the antiproton bump coming from dark matter. But I think it is plausible that you would see a signal. So this red line is showing like a range of predictions for this. So this is trying to fit the antiproton excess. This band is showing a range of predictions based on propagation uncertainties, and this solid line is the gap sensitivity. So there's some hope of seeing a counterpart signal there. Okay, last AMSO2 excess, which may be where we pause for the night, and then or I'll just go very quickly through the others and then come back tomorrow. So as I said, AMSO2 has announced the tentative possible detection of 6 anti-helium-3 events and 2 anti-helium-4 events a couple of years ago. This is really hard to explain with essentially any dark matter model. This is from this paper by Paul et al. In 2019. These are their predictions for the amount of helium-3 and amount of helium-4. These bands show the liquid propagation parameters. This is the AMSO2 sensitivity. Like AMSO2 should not be seeing these antiprotons. So it should not be seeing these anti-helium events under the standard approximations. Paul et al. Looked at the possibility that maybe there are clouds of antimatter or anti-stars in our galaxy. What I took from their paper is that it seems pretty hard to explain how you would form these things so isolated from the matter such that they would not already have annihilated away. That maybe is possible. But there was alternatively this recent theoretical work that suggested basically that our estimates of the anti-helium yield from dark matter annihilation might be systematically underestimated. Like the generators like Pithier and Herwig plus this, plus the prescription that is normally used, could be missing a process which is the production of lambda B bar baryons during the hadronization after the annihilation of decay, followed by those baryons decaying into antihelium. And so these are their like revisited yields. So this purple line is a version of Pythia that's been tuned to try to capture this process. And this red line is the AMSO2 sensitivity. So it's like, maybe you would be able to see a signal in AMSO2 with this. This is a function of rigidity. However, I will note this green line is per week. This yellow line is like per week plus another piece to try to capture this process. So the event generators are not giving the same answer for this process at the moment. So this is a place where the theoretical uncertainties may be large enough to make the difference between, is it possible we're seeing a dark matter signal, and no chance. So again, something to keep an eye on. If any of you work on event generators and are interested in looking into this, then maybe it's an interesting thing to look into. Okay. Will I do 5 more minutes or? Okay, 5 more minutes. So, we'll see how fast we can go when there are no questions. But I like your questions, they're awesome, and let's have a good discussion about this tomorrow. So I'll bring my slides tomorrow so we can go back to all this slowly if people want to talk about anomalies, but of course we can also talk about anything else relevant to the rest of the lectures. Okay, so the 3.5 kV line is an apparent X-ray spectral line. It was observed originally in a stacked collection of galaxy clusters. So this was the analysis that I mentioned before, where you can look at galaxy clusters at different redshifts. You see a signal from each of them. You redshift each of the signals appropriately, and then you see if they line up in the same place. And that's an internal consistency check that what you're looking at is really coming from the clusters and not coming from like there is a bug in your detector that causes ghost photons at some energy. So I'll pass that test. The individual signals were moderately significant of about 4 sigma each, but since then there have been a bunch of follow-up studies which found apparent counterpart signals in the inner part of the Milky Way galaxy and also in the outskirts of the Milky Way galaxy. And this is from a review by Kev Abazagian in 2017, where each of these colored contours is estimating the parameter space that you would need to match the excess seen in a different region. So like this purple region is analysis of the Chandra deep fields, which is part of the Milky Way halo. These green and blue lines are results from green and blue and pink lines are results from different clusters. The x-axis here is, this is assuming that you've got a 7 keV dark matter particle that's decaying away and half the energy is going into this photon. So this is mass on the x-axis, and this y-axis is a measure of the coupling strength. It's expressed as like a mixing angle between the sterile neutrino and the neutrino. So okay, so and we could translate this into a decay lifetime, and it would correspond to about like 10 to the 28 or 10 to the 29 seconds for this preferred region. Okay, so these observations are, there are significant errors on them. None of them are super significant. They're all sort of around this like 3 or 4 sigma range, but they look broadly consistent. However, now this is the simplest dark matter explanation, but there was a fair bit of model building over the years on alternative dark matter explanations that may be more complicated. I'm not going to go into those in depth at the moment. We can chat about them more tomorrow if people are interested. There are possible non-dark matter contributions here. We know that there are atomic lines from various elements in this rough energy range. And there are also there can also be charge exchange reactions between heavy nuclei and the neutral gas, which this was confirmed experimentally, and the energies of these transitions were measured in this paper from 2016. This is like an atomic physics experiment paper. And this can also give rise to a structure of ions around 3.5 keV, which would look like a line given the current energy resolution of the telescopes. So these are the possible backgrounds. The challenges to the dark matter interpretation here are that people have looked in other regions of the sky and seen nothing, where you might expect there to be a signal if you under the simple decaying dark matter hypothesis. Decaying dark matter is great because the signal should just trace the total density of the dark matter, which is exactly what we measure with gravity. So it's very predictive, but some of these studies have looked in regions where you would expect to see a signal and see, well, we don't see anything, and you can rule it out. In particular, this study has gotten a fair bit of attention by Desert et al. It came out in 2018, but was finally published last year. And they have a Git repository where they go through the calculation, and you can go through a simplified version of their calculation. And what they find is that, so this is the plot I was showing earlier with the favored region for the 3.5 keV line, and they claim to exclude everything above this black line. Okay. So that's, yeah. So they claim to exclude the region that's favored for the excess by about an order of magnitude. There's been a debate on the archive about this. And basically the key point is the answer you get depends quite a bit on like what energy range you perform the fit over and how flexible you make your background model. Yeah, I encourage you to read these papers, this paper and these papers if you're interested. And I think there's a response from the authors of this to these, and I don't remember if then there's a subsequent response from these guys to the author, but you know, I suggest reading the debate on the archive if you're interested. This, however, is a place where we have future X-ray experiments that will have much better energy resolution and have the possibility to dig into this with more confidence. In particular, the micro-X experiment is a sounding rocket experiment that has done one flight and could potentially do a dark matter search flight in the next couple of years. Zeta is already flying and should also have the sensitivity to see this signal after a few years. One strategy, which is the topic of the exercise in this part of the chapter, is that if you had good enough energy resolution, you could see the broadening of the line from the velocity of the dark matter particles in the halo. This is like a Doppler shift effect. As you look at dark matter from different parts of the halo, it's moving with a different line of sight velocity relative to you. That will shift the line, and the velocity dispersion of the particles will broaden the line. If you've got good enough energy resolution, you can see this. The energy resolution you need is about 2 or 3 eV, which is very hard, but future experiments have the capacity. Well, experiments that should be coming online within the next 10 years have the capacity to do it. Okay. The last two things that I wanted to mention were edges and the GCE, but those are both kind of longer topics. So I think I'm going to tell, so the very bare bones for edges is what I said already, that the edges experiment sees this deep, claims to see this deep primordial absorption trough for 21 centimeter radiation. And the prediction from standard cosmology would be that the coldest the gas, they say this is coming from redshift 17, and standard cosmology says the coldest the gas should be at redshift 17 if no stars have switched on and there's no heating whatsoever. The only source of heating is the CMB scattering on the electrons, is it should be no colder than about 7 keV. This analysis says that it's less than about 5 keV, sorry, Kelvin, not keV, both begin with K. Should not be colder than, very, very different numbers. Should not be colder than about 7 Kelvin, but this analysis says that it's less than 5 Kelvin at 99% confidence, if everything else about cosmology is unchanged. So this suggests either new physics of some form or a systematic error. These papers are suggesting various possibilities for a systematic error, either in the foreground modeling or in the instrument. And I can tell you more tomorrow if you're interested about the various beyond the standard model possibilities that people have cooked up for what could be causing this. And then the last anomaly that I wanted to mention was the galactic center excess. So this is an excess of gamma rays peaked around 1 to 3 GeV around the inner galaxy. It was discovered in 2009 by Lisa Goodenough and Dan Hooper, confirmed by the Fermi collaboration and this analysis by Agello et al. In 2016. And this is morphologically what it looks like. It looks like a blob around the galactic center. And this is an energy spectrum wise. These data points are showing the energy spectrum of the excess. These are statistical errors only, not systematic. So, and this plot is really sort of illustrative of the galactic center excess. This black line is a dark matter fit to the data. It corresponds to annihilating dark matter with a cross section of 2 × 10 to the minus 26 centimeters cubed per second, annihilating the B blocks, and it looks beautiful, right? However, these dashed lines are the observed spectra of gamma ray pulsars seen by Fermi. And that also looks rather suggestive, especially at the high energy end. At the low energy end, the pulsars don't look as good, but as I said, these are statistical errors only. If I put the systematic error bars in, the systematic errors will be largest at low energies because that's where Fermi's angular resolution is getting really bad and its ability to distinguish signal from background is becoming worse. So, there are also other possibilities for this. You can try to do this by cosmic rays flowing out from the galactic center and scattering on the gaps around the starlight and making gamma rays in this region. But the two leading hypotheses are generally being, maybe we're looking at a thermorelic dark matter signal and the antiproton signal in AMS, the debated antiproton signal in AMS as the counterpart, or maybe we've discovered a new population of pulsars. The very short status update on this is that if you'd asked me 3 years ago, I would have said with 95% confidence we discovered a new population of pulsars. But over the last few years, some of the evidence that appeared to point in that direction has been found to have some systematic errors that were not understood at the time. That doesn't mean it's not pulsars, but the evidence in that direction has I think gotten a bit weaker over the last few years. And yeah, so happy to chat more about that tomorrow, but that is my zero thought status report on the galactic center access. Okay, thanks very much, everyone. I hope you enjoyed these indirect detection lectures. I will see you all tomorrow for further discussion. Please bring questions, and yeah, I'm happy to talk about the anomalies and send you not ask questions for those, but also about anything earlier in the lectures. And yeah, thanks. I mean, I guess I'll say this again tomorrow, but thank you all again. This has been awesome. I really enjoyed chatting with you, and you've asked fantastic questions throughout. Thanks very much.